Here's a rather challenging fluid mechanics problem which looks at the topic of hydrostatics mainly, and it also deals with this idea of stability of a submerged object. Okay, now if you have any suggestions for any similar fluid mechanics problems that you'd like to see, please let me know in the comments. So this is the kind of question that you might get if you're either a first-year engineering student doing something like aerospace, mechanical, ship science, engineering, or even if you're in high school and you're preparing for some kind of physics Olympiad or competition. This might be something that you could potentially see. Now, let's read the question. Let's try to understand what we have to do. So we're dealing with a candle which is floating in water. So the liquid that we're dealing with is pretty straightforward. It's just water, which has this density here, which is 1 gram per centimeter cubed. And it's vertical. Now, in addition to the candle, which is made out of wax, and the wax density is given as this, to the bottom of the candle there is a small cylindrical piece of aluminum, or just an aluminum cylinder, which is attached to the bottom part of the candle. So right here, where I circled it in green. And we know the density of that as well. So the density of the aluminum is 2.7 grams per centimeters cubed. We know the length of that, and by length I mean this distance here. So from here to here we have 1 centimeter. Don't confuse that with the length L, by the way. So the length L refers to the whole candle. This length of 1 centimeter just refers to the aluminum cylinder. Okay, so part A is asking find the maximum and minimum length L of the candle so that it can float in water stably in vertical orientation. Okay, so it has to be vertical, it has to be stable, and it has to float. Okay, those are the important things. And we also know that the radius of the candle is small enough to ignore any horizontal shifting of the point of application of the buoyant force. Okay, so this last bit essentially says that the candle is thin enough so that we don't have to worry about, like the buoyant force being off center or anything like that, or we don't have to worry about basically taking moments about the center of mass of the candle with respect to this radial direction. Okay, so we're gonna call this candle as thin as a result. So here's the tricky part, in my opinion. For part A, we have to figure out the lower and upper bounds of L, right? So we have to say that L has to be between some maximum value, and on the other side it should be bound by a minimum value. But what do those values actually mean? Why is L why is this length L supposed to be bound by, why can it not go above a certain value and why cannot go below another value? And that's what we're going to try to understand. So let's first look at this. So why does L have to be above a certain value? Well, first of all, clearly L has to be greater than 0. Or let's say L has to be greater than or equal to 0, because we're dealing with lengths and lengths cannot be negative. So when L is 0, what we're essentially dealing with is we're just dealing with a cylindrical piece of aluminum which has a height of 0.01 meters. Okay, so we're being told that the length of the cylinder is 1 centimeter, so the same length in SI units is 0.01 meters. Okay, so this is the cylinder. And this corresponds, by the way, to a length of 0 of the candle, of the wax portion of the candle. Okay, now if that's the case, this is not going to float. Okay, because the density of aluminum is 2.7 grams per centimeters cubed, and the density of water is 1 gram per centimeters cubed. And you can see that the density of aluminum is greater than the density of the water. Okay? So it's not going to float. So in that case, let's try making L slightly larger. Now, if we make L slightly larger, so let's use yellow for the candle. And I know that the question says the radius is small, so technically the whole candle should be relatively narrow or thin, but I'm just exaggerating it. I'm just exaggerating a bit just to make things easier to see and understand. So if we add just a tiny bit of wax, it's most likely that this aluminum is still going to be the driving factor of whether or not this is going to float. So if you add just a tiny bit of wax, so this is a bit of wax, let's call it like this, without using any proper mathematical terminology yet, then this will still sink. So why will this still sink? Here's the question. Because whereas the density of the pure aluminum was 2.7 here, if we add a bit of wax, and the density of the wax is 0.8 grams per centimeter squared, if we add a tiny bit of it, the average density is not going to change that much. So maybe this will drop from 2.7 grams per centimeters cubed when we just had aluminum. Maybe this is going to become something like 2.5 grams per centimeters cubed. So the average density will decrease, but not enough. So this kind of gives us a hint on how we have to do this. Now, because the density of the wax, I just noticed the density of wax, and so the wax and the water have the same, they start with the same letter. So let's call this row 0 for the water density, and the wax we'll just leave it as W. Okay. So the condition for the candle to float is for the density of the candle to be less than or equal to the density of the water. Okay, so this is the same as our row 0, which is 1 gram per centimeters cubed. And this is the density of the candle. Now, the density of the candle is the mass of the candle divided by the volume of the candle. And this includes not just the mass of the wax, but also the mass of the aluminum bit. So the mass of the candle looks at the mass of everything that creates that candle, which is the wax and the aluminum. So this MC refers to the mass of the whole thing, and the volume of the candle is, of course, the volume of the whole thing. And this is essentially the average density of the candle as a whole. So for this to float, we must have that the average density should be less than or equal to the density of the water. That's the general condition for any object to float, right? You must have, so for example, if you think of ice, so the reason why ice floats is because the density of ice is less than the density of the water. So the density of ice is somewhere around 0.9 grams per centimeters cubed, and the density of water is 1 gram per centimeters cubed, right? So this is greater than the density of the ice, which means the ice will float. And it's the same reason why oil and water don't mix. It's exactly the same idea. So we must have this condition that has to work. So we must have that the average density should be less than or equal to 1. So let's think about what happens here for a bit. If we have our piece of aluminum just by itself, which has a length of, so this is the length of the wax that's applied to the candle. So obviously if we just have aluminum, then there's no wax, which means L is 0. So in that case, the average density is going to be the density of the aluminum, which is 2.7 grams per centimeters cubed, because we just have aluminum. Okay, now if we have the aluminum and if we add a bit of wax, as we did previously, what's going to happen is, So this is, let's say the new length is maybe 0.2 centimeters, right, of wax. Maybe the average density, now I'm not doing any maths at this point, but I just want to illustrate an idea. So if we add a bit of wax, the average density of the whole thing is going to drop clearly, and maybe it's going to drop to something like 2.4 grams per centimeter cubed. And if we add even a bit more wax, so if we increase this to 1 centimeter, like this, maybe this is going to drop further. I mean, it will definitely drop further, but maybe it's going to drop to something like 2 grams per centimeter cubed. So you can see that the more wax we add, the more we decrease the average density. So the question is, how much wax do we have to add? In other words, what should L be such that the average density becomes 1 gram per centimeter cubed? And this is the minimum length of the candle so that it will be able to float. Okay, so if we add more than this minimum value, right, this is L min, if we add more than this minimum value, the density, the average density will decrease beyond 1, right? So it can be 0.9, 0.8. So it will float more and more of the candle will be out of the water, basically. Okay, so that's what we are trying to do. This is how we find this minimum bound of L, and then we're going to look at how we find the maximum one. So for the minimum value of L, all we have to do is we just draw the candle with the piece of aluminum at the bottom, and we're going to say that at this moment, the candle, the wax part of the candle has an arbitrary length L. So we're trying to find the L such that the average density of this is 1 gram per centimeter cubed. Right. So I usually suggest using symbols rather than numbers, but in this question, as you'll see, it's going to be much easier if we stick to using numbers from the beginning, which I don't really like doing, but it works better just this time. So the length of the cylinder, this portion here is 1 centimeter. The length of the candle of the wax part is L centimeters. This is our unknown. Okay, so let's try to find this average density. So we know the average density is the total mass divided by the total volume. Now the total mass is the mass of wax plus the mass of the aluminum bit divided by the volume of the total volume, which is the volume of wax plus the volume of the aluminum. Right. Now let's rewrite this as follows. So we have the average density equals, now the mass of the wax is the volume of the wax, or let's start with the density. So it's the density of the wax multiplied with the volume. So we're just looking at the volume of this bit. That's the volume of the wax, basically, which is the area. That's this cross-sectional area, which is considered to be small, multiplied by the length, because a candle is essentially a cylinder, right? So you multiply the area with the length and you get the volume. And then you add the density of aluminum. You multiply this by the area times this 1 centimeter here, which is the length of the aluminum cylinder, and you divide that by the volume. So you're going to have A times L, which is the volume of the wax, plus A times 1, which is the volume of the cylinder. And now you can see that the area is actually completely irrelevant. So it cancels out from everywhere. And now I'm going to add in some numbers. So this is equal to the density of the wax, which is 0.8 times L, and then we have plus 2.7 times 1, and this is divided by L plus 1. Now, for this to float, remember, this here is the average density of this object. So for this to float, we must have this less than or equal to 1. Okay, so this is going to be our constraint, and we're gonna move this here, and we're gonna find L. So if we cross multiply, we get 0.8 L plus 2.7 is going to be less than or equal to L plus 1, which means that if I move this to the other side and the one to this side, we end up with 0.2 L is going to be greater than or equal to 1.7, which means that L has to be greater than or equal to 1.7 over 0.2, or just 1.7 times 5, and this is going to be 8.5 centimeters. And that's it. So this is our L min, essentially, right? So if the length of the wax portion of the candle is at least 8.5 centimeters, it means that the average density will be low enough to allow the candle to float. And if we add even more wax to the candle, so if we make this 9 or 10 or 10.5 and so on, then the candle is going to float even more. And what I mean by even more is that the candle will start rising above the surface of the water more and more the more wax we add. Okay, so the aluminum bit is here, and the more wax we add, then the candle is going to rise above the water surface as a result. Okay, so this is L min. Now, how do we find this? Or what is this? Why is L bound from above? Why does the question ask to find the maximum length L of the candle? Because clearly, if we keep adding more wax to the candle, this will clearly float. So that shouldn't be an issue. So the more wax you add, nothing is going to change in terms of the floatability of this candle. So why should we stop at some point? Why should we stop adding wax? Because according to the question again, there is a maximum value that we have to consider. So part A is not just asking about the floatability. So yes, we have that. And it says the candle should float, but it should also float stably in vertical orientation. Okay, so this is the keyword, stably. And let's look at what it means. Now, if you think of ships, right? So if you have if this is the hull of the ship, which is submerged. So typically on the ship, as it's stationary, let's say, you have two forces acting on it. So you have the weight of the ship, and you have the buoyant force, right? So you have the buoyant force like this, and this is the configuration that you should want, right? Because if your center of mass is above where the buoyant force is acting, your object, your ship, is going to be quite unstable, right? So if you're dealing with this, if your buoyant force is acting here, and if your weight is acting here, then this is an unstable situation. And what can happen is, for any small disturbances, if any disturbances happen, the whole ship can capsize. Okay, but here, if any disturbance occurs in this first case, then the ship will return back to its original equilibrium state. So let's try to think what this means for our candle. So let's say you have the water surface like this, and then you have the candle here, and then you have the piece of aluminum stuck to it at the bottom like this. Okay, now this clearly has a weight which is acting through the center of mass, which we don't really know where it is. So the center of mass is going to be, let's say here, this is going to be mg, and then the buoyant force is going to act maybe like this. And we're going to talk about where the buoyant force is acting to. Now, this is a stable configuration. So you want your center of mass to be as low as possible, or at least you want the center of mass to be below the point where the buoyant force is acting, which means that when the center of mass moves, because the center of mass does move in our case, remember we're adding wax to the candle. So the more wax we add, the more the center of mass moves away from the aluminum component, and it creeps upwards towards where there is more wax, basically. Okay, so this is what's actually happening. We have a center of mass that's continuously increasing, but we must constrain it so that it doesn't exceed above where this buoyant force is acting. So if the buoyant force is acting here, which doesn't have to be the same place as here, for example, but if the buoyant force is here, you want your center of mass to be anywhere below that. Okay? And in the limiting case, what's going to happen is if you add enough wax, then the center of mass of the candle and the origin of the buoyant force are going to overlap, right? So they're both going to exist in the same place, right? So one is going to pull down, and the other one, the buoyant force, is going to keep the candle afloat. And if we add even more wax after this, the center of mass will increase, it won't increase, but it will go up even higher. Okay, and then the candle will not be stable anymore. So we want the center of mass to be anywhere below where the buoyant force is acting, and that is our constraint. So if we measure the center of mass from the bottom, this is, let's call it YCM. We want the coordinate of the center of mass to be less than or equal to the coordinate of where the buoyant force is acting. And this is going to give us this value of L, which is L max. Anything above this value of L max will create an unstable floating candle. It will float because it has enough wax, but it will not be stable because the center of mass will be above the origin or the point of application of the buoyant force. Okay, so let's see how we do this. Let's try to draw the floating candle. So I'll say that this here is my maximum L. I don't know how much it is, but I'm saying this is the L max that we're trying to find. So this is L max, like this. And let's say the candle is floating this much above the surface of the water. Okay, so what we'll do now is let's first of all add this here. So this is still 1 centimeter because that's the aluminum. Let's try to find the coordinate of the center of mass with respect to the bottom of the cylinder. Okay, so we're just going to apply the formula, which is the following. So the coordinate of the center of mass of the whole thing equals the mass of the aluminum times the coordinate of the center of mass of the aluminum, which, by the way, is just half a centimeter. Yeah, this is a homogeneous cylinder, so its center of mass is 0.5 centimeters above the very bottom. And then we have plus the mass of the wax times the y coordinate of the wax over, and this is going to be the mass of the aluminum plus the mass of the wax. Okay, so let's try to express this in terms of L. So we have y center of mass equals, now we know from before the mass of the aluminum is the density times area times that length of 1 multiplied by the coordinate, which is YAL, plus now the mass of the wax is going to be this, let's just call it L for simplicity. That's going to be the density of the wax times the area times L times Y of the wax divided by the mass of the aluminum, which is the density times area times 1, plus the mass of the wax, which is rho wax A times L. Okay, so as before, we can cancel out the A's. So this is not part of the problem anymore. And let's actually substitute some numbers just to make things a bit easier. So this is rho AL. So rho AL is the density of aluminum, which is 2.7, multiplied with, this is the y coordinate of the center of mass of the aluminum, which is 0.5. So this is times 0.5 plus, this is the density of the wax, which is 0.8, and this is the coordinate of the center of mass of the wax part. Okay, now the wax, the candle is homogeneous, or I should say the wax section is homogeneous, which means that this is going to be my YW. So the YW, I can write it as follows. It's going to be equal to 1 plus L over 2. Okay, so it's L over 2 from here to here. You add 1 to measure from the bottom, and that's basically it. So this is times 1 plus L over 2. And then on the bottom we have 2.7 plus 0.8 L. And there should be an L on top here as well. Okay, it's this L here that we missed. Okay, so let's see what we can do to maybe simplify this slightly. So this is 2.7 times 0.5, so that's 1.35. And then we have plus 0.8 L plus, so I'm expanding those brackets. So we have 0.8 L plus 0.4 L squared. And this is divided by 2.7 plus 0.8 L. Okay, we finally got the center of mass of the whole thing, of the system. And what we need is we want to say now that the center of mass of the whole thing, which let's say it's going to be somewhere here, maybe. Let's draw it at an arbitrary location. This has to be below the point of application of the buoyant force. Now, where is the buoyant force actually acting? We haven't really discussed this. It's not actually difficult to figure out because the buoyant force only cares about the volume. Okay, so if you have an object which is submerged, let's say this is the free surface, right? And you have an object that is submerged like this. The buoyant force is acting halfway between the free surface and the bottom of the object if you're dealing with something like a rectangle or a cylinder. So it's going to act here, which is the halfway point. So if this is L, then this distance is L over 2. And it's the same in our case. So we have, so this here is the submerged section, which we don't really yet know, and half of that is where the buoyant force is actually acting. And we have to find exactly what that section is. So let's call this capital L. So get rid of this. So what we're trying to find is we're trying to find the length of the submerged uh, part of the candle. Okay, so it would just be, if this is L, then that buoyant force would be acting here, which with respect to the bottom is L over 2. So Y of the buoyant force is capital L over 2, but we don't know L over 2. That's the thing. To find L over 2, we have to apply balance of, or Newton's second law, balance of forces. So we know that while the candle is floating, the mass or the weight of the candle is equal to the weight of the displaced fluid, right? That's Archimedes' principle. So It's the density of the water times G, and then times the submerged volume, which is L times A. Okay, so the total mass of the candle, we have written that several times. So that is the mass of the wax plus the mass of the aluminum. And then this is times G, and that's rho 0 GLA. And then the G's cancel out. Okay, and what we're trying to find, remember, is the capital L. So let's try to do that. Mass of the wax. Again, this is the density of the wax, which is 0.8, multiplied by A, multiplied by L. Okay, that's density times volume, plus, and then we have 2.7 times A times 1, and that equals the density of the water, which is 1 multiplied by L multiplied by A. So as usual, the A's cancel out, which leaves us with L equals 0.8 lowercase l plus 2.7. Okay, and that is our L. So this means that the buoyant force is acting, let's find our diagram. Yeah, so the buoyant force is acting here where the blue dot is, which is halfway from the bottom, halfway of that submerged length from the bottom. So it's this L over 2 that we're interested in. So what we want is we want our center of mass of the candle to be less than L over 2, right? We want the center of mass to be below where the buoyant force is acting. So our condition was that YCM should be less than, or in the limiting case, equal to L over 2. And that's it. This is what's going to allow us to find L max. So YCM is therefore this. So as you can probably expect, this is going to turn into a quadratic equation. So that's 1.35 plus 0.8 L. I have to go back and forth a bit, plus 0.4 L squared over, and then 2.7 plus 0.8 L. Let me just double check. Yeah, everything is fine. And this should be less than or equal to this, which is 0.4 L plus, and then 2.7 over 2 is 1.35. Okay, and that's what we have to solve. Let's add the 2 here. So once again, we're going to cross multiply. So if we cross multiply, we get 1.35, so 1.35 plus 0.8 L plus 0.4 L squared is less than or equal to, and this is going to be 0.4 L plus 1.35 times 2.7 plus 0.8 L. Okay, which gives us 1.35 plus 0.8 L. So from this point onwards, there's no more physics involved. This is just pure maths and solving quadratic equations. So, okay, let's see if we can do this quickly. So 0.8, 0.4 times 0.8 L, this is going to be 0.32 L squared. And then we have plus, this should be, let's see, 0.4 times 2.7 plus 1.35 times 0.8. Yeah, plus 2.16 L plus, and the free term is going to be 3.645. Right. Okay, now let's try to bring everything on one side, and that's going to allow us to find what the solutions are. So let's bring everything to this side, to the left-hand side. So we have 0.08 L squared. So I'm subtracting, I'm doing 0.4 L squared minus 0.32 L squared. And then we have 0.8 minus 2.16. So minus 1.36 L. And we have 1.35 minus 3.645, which is minus 2.295. And this should be less than or equal to 0. Clearly we have to find the roots, but before we find the roots, I'm going to divide everything by 0.08 just to get rid of this here. So this is going to be L squared minus 17L and minus 2.295 divided by that, which is 28.68. Yeah, and this is less than or equal to 0. So let's find the roots. So L12 is going to be 17 plus or minus the square root of b squared minus 4ac, which is 17 squared plus 4 times 28.68 divided by 2. So you'll notice that we have a positive and a negative solution, and let's see what they are. So the negative solution is, so I have 17 squared plus 4 times 28.68. This is to the power half times minus 1 plus 16 over 2. Okay, so the first solution is minus 1.546, which makes no physical sense, so we can just discard that. And the other one is, let's see, so 28.68 times 4 plus 17 squared plus 17 divided by 2, and this is 18.54, and that's it. This is centimeters. This is centimeters as well. Okay, so this is the correct solution, basically. Not the correct solution, but the correct roots. Now, our solution is given by the fact that in the limiting case, in other words, when this is actually equal to 0, right? So when we replace the less than or equal to with equal to, then we end up with L max of 18.54 centimeters. So at this length, or beyond this length, if we go to, let's say, 21 or 20 centimeters, the candle will still float, but it will be unstable. Okay, why will it be unstable? Because the center of mass will be too high. The center of mass, if we keep adding more wax to this candle, will look like this. So if we add too much wax, we have the aluminum block here. We have a buoyant force which is going to act here at this point, but the center of mass might be here, which creates instability. Okay, and at this, when the length of the candle is 18.54 centimeters, the center of mass and the point of application of the buoyant force will overlap. And that's it. That's the L max. And now we can finally say that L has to be less than or equal to this value of 18.54. And for the candle to float, this must be greater than, I think it was 8.5 centimeters. Yes, that's it, 8.5 centimeters. And that's part A, which was actually quite long, which was very long, but this is how you approach this. You have to think in terms of the actual physics. So what does minimum or maximum, or why do we need to have a minimum or a maximum length of the wax part of the candle? Okay, now for part B, I think this should be relatively straightforward. So it says when the candle is lit, it consumes wax. And if consumption of wax reduces the length of the candle at a constant rate of 1 millimeter per minute, and the initial length of the candle is 12 centimeters, how long can the candle be used for lighting? How long can the candle be used for lighting? Always floating vertically. Okay, so what this is saying is that in part B, what we have to do is we have to find the time the candle can float if its initial length is 12 centimeters, and if it starts melting, so we light the candle and the wax starts melting at a rate of 1 millimeter per minute. So we have that the initial length, or the L0, is 12 centimeters. We know the final length as 8.5 centimeters, because if the candle becomes shorter than 8.5 centimeters, it will not be able to float anymore. So let's write what the length of the candle will be as a function of time. So that's going to be the initial length minus, and then we have the velocity times time. So it's sort of like a kinematics problem. Now the velocity is 1 millimeter per minute. So this is how fast the candle is melting, which is 0.1 centimeters per minute. So all we have to do is just rearrange. Now we will set this to 8.5, which is the final length. This is 12. This is 0.1. So we just have to find t from here. So let's do just that. So we rearrange and we get t equals to L0 minus L final over V. So t will be 12 minus 8.5 over 0.1. And this should be, let's see, 12 minus 8.5 by 0.1, 35 minutes. This is how long the candle can float while it's melting and until it reaches this final length. And that's the end of the question.